All right, we are back at AP Review. This is 2016 BC Free Response 4. Consider the differential equation dy dx equals x squared minus 1 half y. Full stop. First thing to notice, this is non-separable. You can't separate the x's and the y's, so you cannot be asked to solve this differential equation. They can ask you to do a bunch of stuff. They can make you derive this, but they can't make you integrate. So just kind of keep that on your radar. Part A, find d squared y dx squared in terms of x and y. Cool. So part A, we're going to go ahead and find the second derivative. So when I derive dy dx, I'm going to get d squared y dx squared. And that's going to equal, when I derive x squared, I'm going to get a 2x. When I derive 1 half y, I'm going to get a 1 half dy dx. So that's not wrong, but it's not what they asked me for. They asked me for this in terms of x and y, so I'm going to have to take this guy and replace him with this whole thing, which is the same as dy dx. So the answer that they want is d squared y dx squared equals 2x minus 1 half times the quantity x squared minus 1 half y. Now, that's a right answer, and if you want to stop there, that's fine. If you want to distribute and clean up, that's also fine. But remember, if you multiply and do something wrong, that's on you, man. So I would stop, because if you multiply and do something wrong, you went from having a yes to a no, and that is unfortunate. Part B. Let y equals f of x be the particular solution to the given differential equation whose graph passes through the point negative 2, 8. Does the graph have a relative minimum, maximum, or neither at the point negative 2, 8? Okay, so this is classic second derivative test here, right? So quick review of the second derivative test. If you have a derivative y prime that is 0, right, meaning that y is flat, right? It has a horizontal tangent, right? Like, for lack of a better way to say it, y is level or flat. Then the sign of y double prime tells you about whether the graph has a max or a min. So if that's true, right? So if that's true, if y double prime is greater than 0, then that means y is concave up, and what you're looking at is a min, right? And if y double prime is less than 0, then your graph is concave down, and what you're looking at that flat point must be a max, right? If y double prime is 0, the second derivative test is inconclusive and you have to pick a different option. So the reason they're asking you to do this in B is you totally just found the second derivative, right? So now in B, what they're asking you to do, right, at negative 2, 8, right, the first thing you should do is check and see what dy dx is at negative 2, 8. If dy dx is non-zero, then the answer is that this is neither a max nor a min, because this is not one of those critical values. So if I plug this in, I'm going to plug in negative 2 for x, and I'm going to get a 4, right? Negative 2 squared should be a positive 4, minus a 1 half times an 8. Oh yeah, that's definitely 4 minus 4, so it's 0, right? So the first part of my second derivative test, totally a 0, that's great, right? What this tells me is that the graph has a horizontal tangent, right? Horizontal tangent, which is the same thing as saying the graph is flat, right? The graph is flat or level. Okay. The second thing I'm going to do is I'm going to check d squared y dx squared, right? And now keep in mind, if you had done part A incorrectly, then you might get the wrong answer to part B, but you could still get the points if your justification is correct. If you use your d squared y dx squared and you got an answer that is correct based on that, you could arguably still get the points even though you messed up part A. Okay, so when I plug in here, right, I already know what number this is, so I'm just going to be super lazy and call that a 0. I'm going to get 2 times negative 2, right, minus a 1 half times a thing that I just did a lot of work to show is a 0. So I get a negative 4, which is less than 0. So the situation I'm looking at is that I have a concave down curve that has a level spot, that's a max. So since dy dx at negative 2, 8 is 0, and d squared y dx squared at negative 2, 8 is less than 0, it's a max. And if you want, you can say by the second derivative test, but you don't have to, right? By the second derivative test. Now, there are other ways to figure it out, maybe, but I doubt it, because it's not like you can make a sign chart for dy dx, because it's not solved for anything. Yeah, so that's pretty much it. That's asking you to use the second derivative test. Part C. Let y equals g of x be the particular solution to the given differential equation with the answer g of g of negative 1 equal to 2. Find the limit as x approaches negative 1 of g of x minus 2 all over a 3 times an x plus 1 quantity squared. Show the work that leads to your answer. I feel fairly certain, that this is leading us down a L'Hopital rule, but I can't swear to it. All right. So, part C, right? We know that y equals g of x is a solution. We know that g of -1 is a 2, right? And they ask us to evaluate the limit as x approaches -1 of the quantity g of x minus 2. I don't know if you guys can hear that, but there is a dog barking downstairs and a toddler shaking a gate and going insane. So maybe you can't hear it, but it is very distracting on my end. The big dog, on the other hand, is sleeping like 6 inches from the computer and totally chill. So that's nice. All right. Okay, so we're asked to find this limit, right? So the first thing we should do is try and plug in, right? If we try to plug in, right? So you always try to plug in first, and when you do, you're going to get a -1 here. So g of -1, which is 2 minus 2, so that's a 0 on the top. And when you plug it on the bottom, you're going to get a 3 times a 0 squared, which is a 0 on the bottom. And that is never, ever, 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 ever the answer, right? That is an indeterminate form, right? So indeterminate, that's not how you spell any of those words. Indeterminate form. Right? So, meaning it's not a number, it's not the answer. So, what it does give us the free pass to do, though, is use L'Hopital's, right? I just like to write L-hop, but it's totally L'Hopital's rule, right? I'm just super lazy, and I write LOP. So, we're going to go ahead and use L'Hopital's, right? And what L'Hopital says is that we're allowed to just make this thing, right? So this thing is equal to the limit as x approaches -1 of the derivative of the top, which would be g prime of x, minus a 0, so who cares about that, over the derivative of the bottom, which would be a 6x plus 1 quantity to the first, right? So, great, very cool. So now I'm going to go ahead and try and plug in here and see if I get a 0 again, right? Well, I know that g prime, right, is happening at the point -1, 2, and I know from the original diffie-q I was given, dy dx evaluated at -1, 2 should be a 1 minus a 1/2 times a 2, which is totally a 1 minus a 1, so oh hey, that's still a 0. And I can see on the bottom that I get a 6 times a 0. Oh look, it's 0 over 0. Please see the thing where I mentioned how that is never ever the answer. So I guess we're okay to L'Hopital again. So we L'Hopital again, right? So I'm allowed to say that this is equal to the limit as x approaches -1 of g double prime of x over, and when I derive this guy, I just get a 6. So now, I just need to know what g double prime is. Well, g double prime is the second derivative, which we totally found in part A, evaluated at this -1, 2, right? Well, that, oh my, don't you wish you didn't erase this off the board, Hogan? That is going to be a 2x, so 2 times -1, minus a 1/2 times what used to be dy dx, but we already found that dy dx right up here, right? We found dy dx at this point was a 0. So I end up getting that this is a -2. So this ends up being a -2 over 6. Oh, look, that's a number. -1/3 should be my answer. Right, so it's 2 applications of L'Hopital's rule. Good times. Oh, and it's L'Hopital's with an S. I just always forget because it's silent. So, L'Hopital's. It looks like La Hospital's, but it's L'Hopital's. Cool. Part D. Let y equals h of x be the particular solution to the given differential equation with h of 0 equals 2. Use Euler's method, starting at x equals 0, with 2 steps of equal size to approximate h of 1. Cool. So, they're just all about giving you different solutions to this non-separable differential equation. All right, so when I do Euler's as a table. Not everybody does. I just am organizationally challenged. It's x squared minus 1/2 y. Okay, so what they gave us in part D is that h of 0 is 2, right? And they ask us to approximate h of 1 in 2 equal steps, right? So I'm going from 0 to 1, right? So from 0 to 1 in 2 steps means I'm going by 0.5, right? Because it's 1 minus 0 divided by 2, which would be a step size of 0.5. So when I make my little table, and again, not everybody uses a table, it's just kind of my jam. I know that the original point is 0, 2, right? I know that my slope is x squared minus 1/2 y, right? And then I use point slope, essentially, because that's really what Euler's is, to find my new y, right? it's the slope times x minus the x value, which would just be delta x, which in this case is a 0.5, right? Plus the y old, right? And again, what I do to get that, and I've done this in other videos too, Euler's is basically y minus the y value equals mx minus the x value. That's point slope. And then you add the y over. So you get y equals mx minus the other x value, that's change in x, plus the other y, right? So anyway, so that's what we do. And then I'm going to do it in a couple steps. I'm going to do a 0.5, and I'm going to do a 1. And my final answer is just whatever y value I get when I get here, right? So to find the slope, right, I plug in 0, 2, and I get that this slope is a 0 minus a 1/2 of a 2, so that's a -1. So that means my new y, that's going to go in this spot, is the slope, -1 times a 0.5, plus the old y, which was a 2. So that's a -0.5, right, which is -0.5 plus a 2, so that's a 1.5. So I get a 1.5 here, right? And then I do the same thing again, right? So I get an x squared, so my slope is x squared, which is going to be 0.25, right? Minus half of a 1.5 is a 0.75, so I end up getting a slope that is -0.5. So now my new y, which is going to end up being my final answer, is a -0.5 times a regular 0.5 plus the 1.5. Well, that's a -0.25 plus a 1.5, which gives me a 1.25. Now, if you don't love decimals, you could totally have done this as fractions and you would get a 5/4, and that's totally fine. When you do an Euler's problem, they generally give you at least 1 point just for doing the number of rounds of Euler's that they requested, knowing that sometimes your adding goes awry.